So let's look over here. So let's look at number 1. Again, let me tell you how, the quiz today. What's going to be on it. I'll be checking all this. All of your grades are going to be worth, give me 1 second. They're going to be worth 5 points. So, sorry, bud. Come down a bit. There we go. Okay. Okay? Yeah, units are definitely what we want. Okay.
That's my bad.
Yeah, that's good. So, number 1 is correct. I have my givens, my equation. Perfect. Well done. Number 2, again, is correct. You have all the 5 parts. Only thing I really want you to think about. This kind of shows me you really don't have quite the understanding. Remember I told you you only have one numerator, one denominator. I see a numerator, denominator there. You can't have that. Okay? This meters per second really needs meters per second, like over there. It's meters per second. One numerator, one denominator. That's how these meters cancel out and you get hertz. If you don't do that, that will be a point off because you cannot have that. Okay, so please make sure that you are keeping an eye on that. Number 3 is 1 times 10 to the 8th meters. Well done. Units, let's see, only your givens are there. Good job. Let's see, number 4, 2.34 times 10 to the negative 9th meters. Okay, good. And number 5, let's see. Put that in your calculator for me. You got it set up right, but that answer is wrong. So let me see it in your calculator and see what you did. It should be 4.04 times 10 to the 12th. So look over here. I'm assuming this is number 6. Yep. So 1.15 times 10 to the 7th hertz. Good. Number 7, 6.9 times 10 to the negative 8th hertz. Yay. No, it's meters. Guys, you have to know your units. And if we're looking for wavelength, it has to be meters. But I would mark off a couple points off this because I see givens and I see answer, but I don't see your equation or your substitutions. So you lose 2 out of 5 points. I need you to close up all your Chromebooks. There's no reason to have them open right now. I don't care. We don't have game day. So close your Chromebook, please. Okay. Okay. So 8, 1.42 times 10 to the 5th hertz, and 9 is 5.3. I got, okay, so 5.36 times 10 to the 3rd hertz. Good. And then finally, the wavelength is 2.74. You had to get it to hertz, so I took off a few points for that because you can't use megahertz. Your basic unit for this is hertz, so you need to make that so hertz, megahertz, and then 1 and 10 to the 6th. Okay, so please make sure you're aware of what you're doing with those. Okay. More the important thing. Okay, electromagnetic radiation. This is energy that travels through space. Only radiation has the ability to travel through space. It's the only energy that can. Heat can't go, we have, remember, conduction, convection, and radiation. Radiations can travel through space. And we talk about it in terms of wavelength and frequency. You now know wavelength, you now know frequency, and we know that you multiply the two, the product is the speed of light. And the speed of light is 3 times 10 to the 8th meters per second. All of this electromagnetic radiation comes from the sun. Our sun produces all this. Let's see right there, that's good. All these different radiations, they get blown towards the earth by the solar wind, and then, of course, it gets pulled in the earth by our gravitational magnetic sphere. Okay? Yes? We good? Okay. Let me grab my clicker. Oh well. Okay. I like this picture. This picture shows you, here's the sun and all the different radiations coming off of it. And I also like the fact that it shows you the length of the wave, and it gets smaller and smaller and smaller and smaller, down to it's the frequency is great, the wavelength is really small. This is the gamma radiation region, which the higher the frequency, the more the energy, and the greater the danger. So I kind of like this because it just shows you how it comes out from the sun. It's nice. Okay, so we look at the electromagnetic spectrum. The electromagnetic spectrum just gives us a spectrum. Just how far between, goes from low to highest. It's a way of ordering these different radiations. From low to high, from low wavelength or long wavelength to short wavelength, from low frequency to great frequency, low energy to high energy. It's just a way of organizing it. Okay? So that's what the electromagnetic spectrum is. So it ranges all these different radiations for us. And this is a quick movie we're going to watch on electromagnetic radiation. I think it's really good. I'm going to turn this thing off. Here. Of the electromagnetic spectrum, because it kind of gives you an idea of the size. You can sit back down if you want, as long as you keep your eyes open, okay? This shows the nice wavelength. It also shows you the size of the different waves. Radio waves can be the size of a mountain, can be the size of a building. They're big, long waves. They have very low energy, very low frequency. They can't hurt us. They're probably around this room right now, as they showed you. If you could see all the radiation, all the waves around you right now, and you put your hand in front of your face, you probably wouldn't be able to see your hand. They're all around you right now. And then comes the microwave. Microwave is a little bit shorter wavelength, not too much so. It's about the size of an ant. That's why it still can't hurt you. Okay, it can't hurt us because it can't penetrate our cells. For something to hurt us or damage us, it has to be able to penetrate our DNA, our atomic structure, our cells in general. And those can't. So when people say, oh, you're going to get cancer from microwaves, no, you can't. It's bouncing off your skin, but it's not penetrating your skin. Infrared is the next one, about the size of a needle eye to maybe a protozoa. Again, it's too big for us to see. For us to see anything, it has to go through our iris, cornea, iris, strike the back of your eye, hit your retina, stimulate the cones, the rods, send electrical signal to your brain, which then flips it over and does some things, and you see things. Infrared is too big. It can't make it into our eye. It can't make it into this area where we need to see. But we've designed, tools to see infrared. We can feel infrared. It feels like heat. That's infrared. But we just can't see it. Then comes visible light. Visible light is between the size of a protozoan and a virus. This is the size that can actually penetrate our eyes and allow us to see things. Oh yeah, hang on.
I got a question. Are you busy teaching right now?
Yes, I am.
Okay, well then never mind.
You just want to take pictures if you want to.
Well, I need like
action.
I need like people to make a shape.
Oh, okay. I'm sorry.
I'm thinking of like doing like gradually bigger and bigger shape with different people. So.
But anyway, so visible light is small enough it can get into our eye and we can see it. What we really see is the reflection of the waves. If something it doesn't reflect, we can't see it. So when I look at your red shirt, everything else is being absorbed. All the other wavelengths are being absorbed, and only red is bouncing back to my eye, and that's why I see red. But what this amazes me is the fact that I see a plethora of colors here, such a variable group of colors, all at the same time. I mean, the eye is a spectacular organ, and I just can't imagine all the nerve endings and all the chemical reactions and everything that goes into it to make us see. Just craziness. And then comes UV. This is where it starts getting dangerous. visible light isn't a problem, but once you go a little bit smaller than visible light is when we start becoming more impacted by that wavelength. Because UV radiation can penetrate our cells. You know, if you go out in the sun, you get a sunburn, that's because UVA and UVB are striking your skin and they're causing it to get hot and it's burning it. It's vibrating your skins and burning your skin cells. UVB, you get enough of it, it goes through. You have these melanin cells in your skin to protect you. And of course, with our losing our ozone layer, with all the climate changes and issues like that, more UVBs coming through. We're getting more broad spectrum UV rays. And it's striking our skin, it's shaking the melanin cells, and sometimes they can't turn off. They shake and turn brown to protect you from the sun. They're absorbing the UV. But after a while, they maybe don't turn themselves off, and then you get melanoma. Melanoma is one of the number one cancers that's happening today. It's also probably one of the number one most preventable cancers of today. I mean, my friend who teaches in San Diego, she loses maybe a kid every few years to melanoma. High schoolers. Because they go out and they surf, they hang out in the sun. They're in California. They don't use sunscreen. You guys come prom, it just drives me crazy because I'm like, oh my God, don't get in those tanning beds. You don't need to be in those tanning beds. You're beautiful the color you are. You don't need to be tan. You know, I go to Planet Fitness and I just want to drag people out of those tanning beds in there. I'm like, when I like walk around a little sign going, you know, you're frying your cells. Because UV can go in and actually shake up your DNA and your cells and click them on. You know, and sometimes you don't know you have melanoma until it's too late. As I said, my father passed away of melanoma 5 weeks after they detected it. There was nothing they could do. He was part Cherokee. It gets really dark. He had a mole on his back. They didn't even know he had it because they just never saw it until he had the flu. He was 53 years old. Thought he had the flu. I'm 2 years younger than what I am now. A year younger, really. But you know, they said, oh no, it's not, it's melanoma, and it's now in stage 4 through your whole body, and you've got 6 months to live. He's like, what? And he only made 5 weeks. So we buried him in January. So it could be prevented. You know, and I'm my father, I get very dark. I've got so many scars on my body from taking off melanoma, and the one on my face was a basal cell carcinoma. And they took out this much of my face. It was horrible for a while. But I went to try to donate a kidney to a friend of mine who really needed it. And I'm not a possible candidate because I've had a cancer. Just because I've had basal cell carcinoma, I'm now off the organ donor list, which makes me very sad. So it not only impacted me, it impacted my friend, it impacts people. Try to be aware. And this is my little PSA. I always tell my dermatologist, I'll do this for him, you know, to try to make you aware of skin cancer. UV radiation is one of the worst because it comes to us. It gets through, and it's harmful. We can prevent it. You just got to wear sunscreen, wear loose clothes, hats, whatever. You know, you don't have to, like, not go out in the sun. You just have to be smart about it, okay? And also, because it can also get in your eye as well. My cat had melanoma of the eye and died from a brain tumor. It went to her. I was like, what? Her eye turned all black. And I took her to the vet. I'm like, her eyes just, it looked like she had her whole you know, the iris was her whole eye. I'm like, he said, no, that's melanoma. I'm like, a cat? Melanoma from a cat? And he said, yeah. It was slow growing. So she lived like, you know, to be 18, but eventually it just kind of took over and it was very kind of sad. It was like weird. But so anyway, then X-ray. Of course, X-rays don't make it here, thank goodness. We'd all be zapped if we, you know, had X-rays all around us. They stop at the atmosphere, but we harness them. We use them. There's naturally occurring radioisotopes that are here on Earth, and they give off X-rays, and we can generate X-rays, and we use them for our own benefit, for health, and for diagnostic tests and things like that. And of course, gamma radiation, which is the size of an atomic nuclei. protons and neutrons. High energy, very dangerous. We use it for cancer treatment for the most part. That's my niece is giving off right now in my spare bedroom in my house is a bunch of gamma radiation. She got, yesterday was her first pill, or only pill, but first night. So she sat about where Lexi's sitting in her bedroom, and I went down the hallway. I got her Chinese, and I put it outside her door, and I knocked, I backed up, and so I had to sat on the floor with my Chinese, and she sat there with her Chinese, and we were just sitting there eating our dinner, talking, because I have to stay 6 feet away from her at least. So it was pretty funny, because we're like, so, what? Talking down the hallway, and then my cat broke through, and I probably should be recording all this. My cat broke through, and anyway, and we had to try to get him out of that room before the cat got radiated. But she doesn't glow in the dark. I turned off the lights. I was like, do you glow? She's, I don't know. I went, turn off all the lights. Let's see if you glow. She does not. I'm very sad. But I know. So I'm like, Ms. Mitchell's bringing me a Geiger counter on Monday. So it picks up radiation. It's, So I'm really curious to see if she's, I'll videotape it when I go home and do it. It'll be funny to see if she's very radioactive. But it cracks me up though, because, we just keep her down the end of the hallway in her own bathroom, and she's like, I feel so dirty. I said, you're not dirty, you're just contaminated, So don't worry about that part. I know, it makes me laugh, but God love her. Anyway, so I kind of like this. This shows you, radio waves. The guys talk on the microphone. We cook with microwaves. We talk on the phone. Here's my radiated cat in front of the infrared, in front of the heater. Visible light, ultraviolet. She got sunburned. Radiation for that. Gamma, your cancer treatments, and of course cosmic radiations, which really isn't here because it's, it's up in the cosmos. Back in the day when the astronauts used to land from going to space, they'd come down the ocean, but then they'd get them out of the capsule and they'd wrap them in like this metallic type of foil, like a blanket, and then they'd be in isolation for like 5 weeks because of cosmic radiation. Now they get off the shuttle and they walk out and they're done. So I'm not quite sure what's changed between those times, but yeah, back in the day, like, oh no, they're all radiated because they've been in space, but I'm not quite sure. I know there's cosmic radiation out there, but I just don't know more about it. Okay, so the only thing you'll have to know, you won't have to memorize these. I'll just ask you, like, what has more energy, microwaves or gamma radiation? Which one? Gamma. Which is more dangerous, infrared or UV? UV. So questions like that. And you'll have the electromagnetic spectrum, the chart up behind Sam there, to look at. It's not that big of a deal. Okay? But I want you to make it, because you'll see more of these as you get older and things happen. So I just want to make sure you're aware of this chart. Okay. Then we talk about white light. White light is part of the electromagnetic spectrum. So we're going to kind of get rid of all the other radiations and focus on white light right now. Okay? Just visible light. So we know when it goes through a prism, it gives off a rainbow. This is called a continuous spectrum, where one color just kind of bleeds into another color. And we'll kind of get that here in a little bit. So the visible spectrum is right here. It's like from 450 nanometers to 700 nanometers. That's all we can see. That's all that fits into our eye. And of course, here's the visible spectrum. And red has the longest wavelength, therefore the less frequency, less energy. That's why if you ever develop film, there's always a red light in there, not a blue light. Blue light will expose the film, where red won't. So that's why you can keep a red light in there and it won't do anything to the film. There's not enough energy to make the film develop. But blue, there would be. In fact, my nephew called me and said, Aunt Meg, don't forget, keep your cameras away from your DSLR away from Laura, because she'll expose all the stuff in there. I didn't even think about giving her a camera. So, kind of weird. Okay, particle nature of light. Okay, now, how does this all do anything? Okay, here's the fun part. So, why do we care so much about light? We care so much about light because we only understand how light interacts with matter. We know it bounces off. We know it reflects. We know we can see it. We know it gets absorbed. We know these things about light, but there's some things that really kind of were strange for early scientists. It failed to explain how light interacts with matter on more of an atomic level. For example, this, coal burning, that's wood. Where does light come from? How does light come out of a piece of wood? A tree that grew, and now light is coming out of it. How does light come out of something that's matter? Light is a wave. How can you get wavelengths out of matter? You go, well, you put it in fire. Well, yeah, but then how do you explain this? How does a piece of metal glow when you run electricity through it? What makes that glow yellow? And then on my heating coil, that still glows orange. There is no light in matter. How can light come out of something that doesn't have light in it? If light is a radiation, how does light come out of things? I mean, why is it when you put earth and clay into an oven, it starts to glow yellow? There was no yellow light in there when I put it in there. Where? Sorry, I got excited. Where is that light coming from? Well, what they found out is this. Light interacts with matter on the electronic level, on the very particle base level. They found out that certain colors emit that color because of the temperature it is. This is one temperature, this red is another temperature, this purple color is another temperature, and so on. So as the object gets hotter, the colors change. That's why when you give something more air and it gets hotter, it goes from that yellow flame to a nice blue flame, to almost a teal blue flame. Okay? Colors indicate temperature, which is weird. How can light indicate the temperature, especially temperature from matter? Craziness. So we looked at the different wavelengths. So we have this long wavelength here, it's about 1800 Kelvin. As it gets more and more into the blue range, it goes up to 160,000 Kelvin. No, 16,000 Kelvin. Okay, sorry, my bad. So from 1800 to 16,000 Kelvin. The blue is a higher temperature than the red. Back in the day when you say, be careful, it's red hot. It's because it glowed red when it was hot. I don't know many things that glow blue when they're hot, typically. You know, at least around the house or whatever. So that's where the red hot comes from. Anyway, so how does light come out of matter? What makes it come out of matter? Well, obviously something has to excite it. Something has to make that matter more energetic. Okay? Has to make it more energetic. Well, Max Planck came up with this idea. Come on, baby girls. Came up with this idea that matter can absorb or emit, give off, energy in certain amounts. Just certain amounts. That's it. He said it can gain or lose energy in small, specific amounts. That's it. And he called these amounts quanta. Quanta is Latin for fixed amounts. It's like when I go to Myers. I don't walk into Myers and buy my bread by the slice. I can't walk up to the counter and say, here, I want 2 pieces of bread. And the lady would say, I'm sorry, we sell them by the loaf. Well, no, I don't want a loaf. I just want 2 pieces of bread. Sorry. The packaging is a loaf. So that's my quanta, a loaf of bread. You know, when I get on the elevator and I hit the 3rd floor, floors are my quanta. I can't choose to get on 3 3/4 floor. You know, it's not like Harry Potter and 9 3/4, you know, with platforms. This can't happen. Okay? There's certain specific amounts that we can emit or absorb. Does that make sense? Yes? Okay. Just like this. I had to bring this in because I love M&Ms. I buy my M&Ms in little fun-sized packages. I don't walk in and say, hey, I only want like 15 M&Ms. I have to buy them in a package, a predetermined number of M&Ms in a package. It's quantified, isn't it? It's a quantity. Quanta means certain amount, a fixed amount. Okay? Now, we're going to watch this video after we do some other things, just because we didn't quite get there earlier. So, light, we know, is nothing but a stream of photons. You're like, well, what's a photon? A photon is a packet of energy. It's just a certain amount of energy. I picture it like a little ball. If you guys ever watched Charmed back in the day with the three sisters, when a demon would come by, they'd do this, a ball of light would be in their hand. Like, oh, it's a photon. You know, that's what I would think. And they throw it at the demons, and the demons go, ah, and they die. But light comes out in photons. So if you had a flashlight, like a horn, but it's supposed to be a flashlight, and it's emitting light, that light is streaming out in little itty bitty packets of energy called photons. You would see light, but if I looked at it on a very, very tiny, tiny, tiny level, it would look like a bunch of little balls, each being a photon. It's a ball of energy. Does that make sense? Okay? And they stream. They just stream by. Where do I go? So Planck said that each one of these little balls of energy or balls of light, I should say, has a certain amount of energy associated with it. Planck said each photon equaled its frequency, which makes sense. Energy, the greater the frequency, the greater the energy, the less the frequency, the less the energy, right? But it just can't be energy equals frequency. There's got to be something in there, because you can't have just an equal amount. So he came up with his own constant, H. H is called Planck's constant. Planck's constant is this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 66, 2, 6. That's Planck's constant. It's not 0, but it's pretty darn close, right? It's like me picking off just, maybe like the wind off of me and saying it's going to be maybe way less, It has very little effect on it, but it has enough of an effect, it's not the same. This is 6.626 times 10 to the negative 34th. That is Planck's constant. Okay? So each little ball quantity of light, called the photon, is this measurement. It's a packet of energy, which is frequency times Planck's constant. It'd be like me saying, okay, if this were my bag of M&Ms, I spilled them out everywhere, each M&M has the energy of 10 calories. So the more M&Ms I eat, the more calories I consume, right? The more photons I have, the more energy I have. Yes?
His constant, is that just H?
H, yes.
Yeah.
H is Planck's constant. Okay? And so Planck's equation is this. The energy of one photon, just one little photon, is equivalent to H times V. Planck's constant times the frequency. Trent, I need you standing up again. I cannot have you sleeping. I'm sorry. Okay? So energy Planck's constant, and frequency. Those are the parts of Planck's equation. Now, energy is measured in joules. Joules is the guy who came up with energy, and it's capital J. Planck's constant is joules times seconds. That's its unit, joules times second, J dot S. Does that make sense? Yes? Okay. So Planck's constant is 6.626 times 10 to the negative 34th J times S. Now sometimes you'll see it 6.63 times 10 to the negative 34th. That's okay too. It's just rounded, which is fine. Any questions so far? Okay. So let's do some equations. How fun, how fun. I love math. Yay. Okay, so the question is this. This equation defines the relationship between energy and frequency, which makes sense. So, the greater the energy, the greater the frequency, the greater, the danger to us. So, tiny water droplets in the air disperse the white light of the sun into a rainbow. Continuous spectrum. What is the energy? So I want to know what the energy is of a photon, of one photon of violet light, if it has a frequency of 7.23 times 10 to the 14th hertz, or S minus 1.
Times.
Okay?
Yeah.
So, we take our H, 6.626 times 10 to the negative 34th joules seconds. Now, if you look at this, that's our givens. And then you need your equation, E equals HV. And then we just plug numbers in. So the energy equals 6.626 times 10 to the negative 34th joule second times 7.23 times 10 to the 14th. Now, if it's S minus 1, where does that S go? In the numerator or denominator?
Denominator.
Denominator. So it goes down here at the bottom. This S cancels out this S, and that's where our joules comes from. Okay, Sam, let's be a little more mature than that, okay?
What?
You know. Okay. So what's my answer? What's the energy of one photon of violet light? Yes, sir. Good. Times 10 to the negative 19th joules. Energy is typically very small. Okay, it's typically very small. Does that make sense?
Yeah.
Okay, good. And what if I said I had 10 photons of this violet light? How would I figure out what the energy would be for that?
10.
If I have 10 photons, what would the energy be?
10 times 6.626.
No. That's Planck's constant. If this is the energy right here, this is of one photon. This is just for one photon. If I have 10 photons, what would I do?
10 each.
Multiply by 10. I would just multiply this thing by 10. Because it's a bunch of different little photons together. Does that make sense?
Yeah.
It's like eating a bag of M&Ms. If each M&M has 10 calories, and I eat a bag of 1,000 of them, I just ate 10,000 calories, didn't I? Okay? I don't know if I could do that. 100 maybe. Okay? Does that make sense?
Yeah.
You good?
Yeah.
Okay. Well, let's then... Oh, here, I keep looking for it.